Okay.
Okay, thank you. So in this presentation, I want to go over three main experiments that we did in order to validate the sensor fusion in the context of automotive application, using three different strategies. So the first one, let me start by showing you some headlines from 2019, just to show how optimistic car maker were at that time about the possibility of having very soon a fully autonomous vehicle on the road. And just the year after, I mean, there was a totally different message. And basically, what happened? Well, probably because they realized that driving or having a fully autonomous vehicle in operation is difficult, because basically driving is a very difficult perception problem. So you have to be able to perceive the environment under any type of condition. Could be even under difficult weather condition, any time of the day, during the night. There's cases where the perception is really easy, and in those cases, I mean, you can solve the autonomous vehicle problem. But in general, we require, in order to be able to drive our vehicle in any condition, we require a very good perception. So as a way to solve that issue, multi-sensor fusion could be one of the possible solutions. So the idea is to be able to exploit the complementarity and the redundancy of the data coming from different sensors. So obviously, this means that you will have to train your network with different input. In order to do so, you must have your multiple sensors calibrated and registered one with respect to the other. And you must design a multi-branch neural network in order to combine the information from the different sensors and come up with a single decision on the detection. So basically, we can identify three strategies for multi-sensor, depending on where you perform the fusion operation: early fusion, late fusion, or mid-level fusion, in which case the fusion occurs at the middle of the network graph. We can add a fourth category, the sequential fusion. In this case, that would be where you process one sensor, and then from the information obtained from that first sensor, you start another validation stage using another sensor. So that would be a sequential way of performing the fusion. But let's focus on the first three. Let's start by looking at the late fusion. So this is the case where you really perform your neural network graph independently on each sensor. You come up with a decision, and the inference result that you obtain must then be combined in order to come up with a final decision. So in the case of late fusion, I mean, one of the difficulties, obviously, to decide how you will merge information coming from the different sensors. So in a first experiment that we perform, we look first at the result from a basic object detection from Lidar. And we look at the quality of the results. That's what this graph showed you. In green, you have the correct detection in the case of car and in case of pedestrian, and as a function of the distance. And in yellow, you have the result of the detection of the in yellow, you see the false positive that occur as a function of the distance. And in red, these are the false negatives. So what we can see from this graph is that if we really want to improve the result of our detection, we should work on the false positive. And this should provide us with a significant gain in performance if we can solve these false positives. So as I said, these results are for LiDAR only. So the idea is to see what happens if I add a camera branch to that network in order to be able to resolve and identify and eliminate the false positives. So this is the late fusion graph. So on the bottom, you have the classic LiDAR object detection graph. And on the top, you have the image stream. And in that case, we want that image stream to perform segmentation, instant segmentation, in order to identify the pedestrian and the car, for example, in the scene. Well, from the image, obviously, you don't have the 3D information. So what we decide to do is to only look at the horizontal angle and try to see in which direction we have detected car, in which direction we have detected pedestrians. And the idea being that, and remember that our objective here is to be able to remove the false positive, so the falsely identified objects, when we identify the wrong object, basically. So the idea is to validate any classification done by the LiDAR stream by using the segmentation mask. So basically, we look at the different angle where there was a detection. And if the LiDAR predicts that there's a pedestrian in that direction, well, that detection must be validated by the camera and will be accepted only if the camera also see a pedestrian in that case. So that was the way to fuse the information from these two networks. So the results we obtained for that are a bit surprising in a sense. We were able, as you can see, if you look at the, when we compare the result from the LiDAR only to the RGB and LiDAR solution, we have been able to improve the quality of the performance in the case of pedestrian, but not in the case of car. And basically, this illustrates well one of the difficulty with late fusion. You have to make a decision at some point. Do you want to make sure that you increase your accuracy? But in order to increase that accuracy, you often have to trade off the recall, so the possibility of detecting all possible objects in your scene. And as an illustration, so one good result that we obtained was, I don't know if you can see at the bottom of this image, there is a container on the right that was identified by the laser as a car, but from the visual image, we were able to reject that false positive. Same thing for the trunk of that tree that was identified as a pedestrian, and this one was also removed. So that's the benefit of increasing accuracy. However, in other cases, like in the following case, you can see that behind one of the cars, there is a pedestrian. And that pedestrian was missed by the camera network. So for that reason, even if it was detected by the LiDAR network, it has been rejected as a possible false positive. So the consequence is that we lose that pedestrian. So we reduce the recall of our network. Okay, so that's for the late fusion. If we look at early fusion, in that case, the idea is to combine the information, the raw data information, right at the beginning. And in order to do that, ideally, you would like your sensor to be as similar as possible in nature. For example, in that case, I have a thermal camera and a visual camera, so it's quite easy to combine them and see the thermal information as just one more channel added to the image. So assuming that they have similar resolution, that should work relatively well. But in general, in order to make the two representation compatible, you often have to lose some information. And in that process, I mean, you reduce the potential of your network to perform well in any condition. So basically what you have in the case of early fusion, you have to find a way to build compatible representation. If we again consider the case of merging camera and Lidar, one way to do it is to transform your Lidar into images. So you can create from the Lidar information, a depth image that would be compatible with your camera image, to which you can add also intensity information. So the power reflected by the laser, and the height map as well. So that way you come up with your combined representation, your early fusion data. So we built a very simple, in that experiment, we built a very simple network. The idea is simply to build a multi-scale representation from the fused data, and coming up with classification and regression after that. One of the questions then is, how do we combine these two representations, the Lidar and the Lidar images and the camera image? Which fusion operator should we use in that case? So that choice of fusion operator applies to any strategy that you would use in order to perform sensor fusion. And what are the possible operators? So you can simply use concatenation. You can simply stack together the different representation and feed that to your network. Or you can perform operation, simple arithmetic operation like addition or multiplication. You can use order statistic, extracting the mean, extracting the max, the median, or using some more elaborated scheme like creating a subnetwork just to perform the fusion, or use a concept that we refer as the learnable fusion. So we use the network as I just present, and we just wanted to compare these different strategies. Just before that, let me just quickly show you what type of fusion subnetwork strategy operator that we can use. So basically, the idea in that case is to create a subgraph, and the role of that subgraph will really be to perform the fusion and learn how to do it. So as you can see, you have two entry points that represent the two input you have that you want to merge together. And basically, you see that one branch will interact with the other on the left side of the graph, and through another transformation, the left branch will interact with the right branch in order to build another representation. So, and then everything is combined to a final output. So the idea is really to build an interaction or learn how these two modalities should interact with each other. And in addition, in most cases, is to try to learn or to build up an attention mechanism within the fusion process itself. So this would be one way of performing the fusion. Another approach would consist in trying to build a complete graph that would combine, that will consider all possible combination between your the two entries of your data. So to be more explicit, so suppose that you have one of your data that is of size n, and the other data vector is of size of n. So you would like to build a m by n matrix, and all the entry of this matrix will be a particular weight that you will apply, and that will represent the interaction between one entry of one sensor and the other entry of the other sensor. So in a sense, this is probably the most general way of building your fusion operator. However, building that m by n or learning the weights of that m by n matrix could be very expensive. So for that reason, you have to use simplification. I won't go into the detail there, but basically, this has been the complexity of this framework has been reduced by using bilinear operation and in order to build a low-rank matrix. Just to come up with the result. So as I said, we use that basic early fusion graph, and we use different fusion operator in order to fuse the data coming from the two sensors. And these are the results we obtain on the KT data set, which basically shows, the first column show you what happens if we have no fusion at all. So we just use the Lidar information, and how the result can be improved using the different strategy. And in that case, we show that using the more general fusion scheme, the MFB, so this is the learnable fusion operator, but leads to the best result in that case. And just to finalize, that's the last fusion strategy. That's the mid-level. And in the case of the mid-level fusion strategy, the idea is basically to perform some processing before performing the fusion, and also process the data once it has been fused. So basically, the fusion will occur in the middle, at the middle of the neural network. So really, if you want to build a scheme like that, you really have to create two independent branches first, and then you combine these two branches. And in that case, so what we had to do, because we were working with a bird's eye view representation and a frontal view representation, so we had to use continuous convolution in order to extract from the 2D image feature that are coming from 3D points. And once you have that, so you build your, you can perform your multi-sensor fusion. And in that case, we use the MFB fusion in order to perform the fusion. And once you have your the result of your fusion, then you can build a classifier. So you have another, you have few other layers that allow you to come up with the classification and the regression result. So these are the results we obtain again on the KT data set. And the idea is to compare again the result we obtain when we apply the multi-sensor fusion scheme. So we obtain relatively good improvement, but probably the idea is that these improvements would be even better if sensor fusion would be used in a context where you have a very difficult perception solution, which is not the case with the KT dataset. So just as a conclusion, so early fusion is probably the best approach when you want to make sure you detect everything. So you want to increase your recall. Late fusion would be used more when you want to increase your accuracy. And mid-level fusion is probably the strategy that could lead to the optimal performance, but it is a scheme that is very difficult to train because you have multiple branches that are combined, and then you have another network to train from the fused information. On that, thank you.
Any questions? So I have a question to begin with. In the current fusion architecture that you proposed, is it possible to see which sensor is contributing to the classification task and the detection task? Because since it's a combined task, probably the camera is capable of doing better in the classification part compared to, say, the localization by the Lidar is usually good.
Yes, it's a very good question, and you're right. I mean, and that's exactly the idea of using sensor fusion, because you want to exploit the complementarity of each sensor. Camera, yes, very good for classification, while the for example, the Lidar would be very good for the 3D localization. The only thing you can do if you want to try to assess the contribution of each is to do an ablation study where you remove one of the sensor and you see what happened with the classification, with the localization, for example. But yes, you're right. That's the kind of experiment that must be performed.
Any other questions?
Yeah, I have a question. I was wondering, like, if for like in terms of safety, if one of the sensors get corrupt, where in the middle of the execution, how would the fusion work?
Well, it depends how you train your system, and again, that's the kind of experiment that must be performed. You must have mechanism that will tell you when one of the sensor is stopped to operate. I guess this is the main point there. In adverse weather condition, very often the performance of each sensor will degrade at different speed depending on the sensor. But you must train your network in those conditions in order to make sure that the network will learn how to react to these cases, and will be able to detect that the information coming from one of the sensors is not reliable anymore.
Okay, so it's mainly you think it's based on training, or I was wondering if we have to model it somehow in the network as well.
Yes, or to monitor at least. You might even consider having a separate network that would assess the reliability of the information coming from one sensor and be able to detect that basically one sensor should be simply turned off.
Okay, yeah, thank you.
So if there are no more questions, let's thank the speaker.